All right, welcome back to part 2 of the confidence interval introduction. In the last video, I ended with you being responsible for finding z-values in the z-table and for interpreting the interval. So let's jump ahead to the next idea. And again, let me get a pen. Got my red pen. Find a z-value for a 90% confidence interval. So we start with our confidence level and we turn that into an alpha. Alpha is always 1 minus the confidence level. So our confidence level should be between 90 and 99%. So the alphas we're going to use this semester are going to range between 10%, which matches with the 90, and 1%, which is the alpha if we were using 99%. So we take that and we split it in half, and we basically get a picture like we were working in the last problem. And so in our picture, we're going to have 90% on the inside, and you're going to have 0.0500 in either tail. Now, typically when I draw probabilities, when I put them in a picture and kind of picture them, I'm going to think of them as 4-digit decimals because that's the kind of value that we look for in our cumulative z-table. So if you go to your cumulative z-table and try to find the value of 0.0500, I happen to have a cumulative z-table in front of me, or sort of in front of me. It's underneath the microphone. I don't want to get that one, but here's one. I'm going to look up 0.0500, and I can't find it. In fact, when I look up and try to find 0.0500, I see two numbers that are close. I see where is it? 0.505. Ooh, that's almost 0.0500, and 0.0495. So it's kind of splitting the difference between the z-score of 1.64 and 1.65. And of course, in my z-table, the value that I'm going to see, this would be a negative 1 point. It's in between negative 0.1 or 1.64 and 1.65. And this would be a positive 1.645. And so when we're working with a 95% confidence level, these numbers are plus and minus 1.96. For a 90%, these numbers are plus and minus 1.645. That's the value that we're going to use as our z-value. That's the value that we're going to slide into the formula. X bar is going to be a value we get from our descriptive statistics. We don't know sigma. We'll plug in a value of S, and we'll know the sample size, or what Excel calls the count. And so it's a math game. And I'll talk about how Excel does the math a little bit later. All right, so here's an example. I'm interested in estimating the average GPA of all students at a private college. Assuming that there's thousands and thousands of students at this private college. I randomly sample 235 of the students and find a sample mean is 3.2. Sample standard deviation is 0.4932. Use this data to calculate. So this is the calculations. Typically, we would ask Excel. What Excel is going to do is going to open up the descriptive statistics that we've seen before. We're going to click on that we want the confidence interval. And I'll show you how to do that in a video in some other video. It's going to ask me my confidence level, and I would put in the value of 92%. But I want to show you where does all this come from. Okay. It would also, what Excel will do, it'll calculate a value of the mean, and then it'll say for the 92% confidence interval, it'll give us this piece here. And we actually have to go and add that and subtract that from the mean to get the endpoints. But here's how the math is done manually. Our alpha for a 92% confidence interval is 0.08. Alpha over 2 is 0.04. And so we get this picture, except this time we're going to put 0.04 in the lower tail, and in the upper tail is the other 0.04. There's your 0.08. So that means the confidence coefficient, or the confidence level in between, is the 92%, or 0.92. And so now you go to the z-table, and you try to find a z-value that has 0.0400. And if I remember correctly, let me go to my z-table. When I look up in my z-table and try to find 0.0400, I don't see it. I see 0.0401, which is really close. I'm going to use that. And that's the z-score, negative 1.75. And so if you have 0.04 in the upper tail, you could find that by looking up the probability 0.96, the less than or equal to probability of 0.96. And again, you're not going to find it exactly. You're going to see 0.9599, which is, again, really, really close. But the z-value that we're going to use for a 92% confidence interval is 1.75. And I got to be real clear. These z-values that we're using, the reason we can use a z-distribution is because we're assuming we have a large sample, which of course we do in this case, and the central limit theorem says go ahead and use normals. When we work with small samples, that's going to change, but for now, large sample 95% gives me 1.96. Large sample 90% gives me 1.645, like we saw in the last slide. Large sample 92%, we're going to use 1.75, but the point is we can find the z-value to use given the confidence level we want. But now it's a math game. Now you're going to take that number and plug it into the formula, and you're going to do the math. And I know everybody's always excited when you're doing the math. I'm plugging in the value of the sample standard deviation, 0.4932. That goes in for S. The sample mean, 3.2. That's what goes in for the mean. The 235, that's my sample size. You get the square root of it. You do the math. And I'm going to go one further. And so now when I'm in class with you guys, if I was teaching you live, I'd be standing in front of you right now. My hands would be about shoulder height, and I would cup my hands so they'd look like the parentheses. And I'd say, here's our confidence interval. It goes from 3.144 to 3.256. That's the calculations. Pretty much what you're going to have to do is this math, because Excel is going to give you the value to sample mean. Excel is going to give you the margin of error for a 92% confidence interval, and you're going to have to add and subtract to get the endpoints. But that's what we need. So that's the calculations. That's the part you're going to be responsible for. I'd like you to be able to find the 1.75 number in the table, or use an Excel for that matter. I'd like you to be able to find the z-value that's necessary. It's not a skill we really, really need for confidence intervals, but it is a skill we're going to need for test hypothesis a little bit later this semester. But that's the calculations. Now we get to interpret that confidence interval. And so there are two typical interpretations we talk of with confidence interval. And because you drew the lucky straw and got me this semester, I'm going to go through three of them with you. There's usually two. There's a practical and there's a theoretical. The practical is kind of the blunt. Where do you think the mean is? Well, I think the mean is there. And you'll hear me probably say in class, I call this the caveman interpretation. What does that mean? Well, caveman. There's a Geico commercial. It used to be on TV. It said, so easy, even a caveman can do it. And they're pointing people to their app. So easy, even a caveman could do it. And they had this guy dressed up as this old-timey caveman, and he kind of came in and used a caveman voice, like, a lot of grunting involved. But the practical interpretation is the caveman. Where do we think the population mean is? The caveman would say, mu, there. And he'd point to the confidence interval and button. Where's mu? Mu, there. Except you don't know this yet, but you are a sophisticated cave person. What do I mean by that? Well, that's where we think the population mean is, but we can do better than think. We're 92% confident that the population mean falls there. That's how we're going to express it. And when you do a practical interpretation, and you see it on the screen right now, there are three pieces to practical interpretations. There's the confidence level, there's the parameter, in this case it's mu, and then there's the numbers. We're 92% confident mu falls between 3.144 and 3.256. However, whenever I talk to people, whenever I give an interpretation of a confidence interval, or interpret a p-value in a test hypothesis, or interpret anything in statistics, if I drop a Greek symbol on them, if I say we're 92% confident mu fall, they're going to look at me like I have three eyes. They're going to be like, what are you talking about? And so I want you, I'm going to grade you, to be very specific. I want you to tell me what mu is in the words of the problem. It's the average GPA. Which students of the 235? No, it's the average of all. We're using a 235 to make a statement about the average of all. That's that inferential technique we've been talking about this semester. Every confidence interval you run into is going to have the same practical interpretation. You're going to hear me do like this little three-step chant. Confidence, parameter, numbers. Confidence, parameter, numbers. Confidence, parameter, numbers. We're 92% confident that mu, in the words of the problem, the average GPA of all students at a private college falls between the numbers 3.144 and 3.256. Every confidence interval you ever run into will have the same kind of practical interpretation. The confidence level changes, the numbers obviously change, but so does the parameter. We're going to be able to work with proportions later this semester. You're going to be able to work with slopes of regression lines. You're going to be able to work with lots and lots of different things. But the way that we interpret confidence intervals will remain consistent. So the first interpretation we want to talk about, and I just talked about, was the confidence the practical interpretation of a confidence interval. The second one actually looks at that confidence statement there and says, all right, what the heck do you mean? What do you mean when you say you're 92% or 95% in another interval or 90%? What do you mean? What's the confidence interval? And that's the theoretical interpretation. And that goes back to the picture we drew in the first video. That picture I put the asterisk on, I called your confidence interval picture. In repeated sampling, 92% of the intervals created would contain mu. And you can see I'm underlining those two parts. This is the theory of every confidence interval. The confidence level may change. When I went through that first example with you, when I drew the picture, we were talking about a 95%. And actually in your notes, don't I have a statement that says, in repeated sampling, 95% of the intervals created would contain mu? I believe that was right underneath that picture. When you're writing theoretical interpretations for me, it's okay for you to write mu. When you're writing practical interpretations, it's not all right for you to write mu. Be specific. Write it in the words of the problem. In repeated sampling, 95% of the confidence intervals created would contain mu is fine in a project. But for the practical, I want you to tell me we're 95% confident that the average mileage of all Mustangs falls between, and give me the numbers. Be specific in the practical. You can be generic. You can be less specific in the theoretical. So those are the two interpretations typically folks want to know about. I'm going to go a step further. I'm going to ask you some questions. And these will come at you either in the form of a question or someone will make a claim and I'll ask you, what do you think about the claim? And I didn't do my animations correctly, so let me pause and fix that. All right, let's see if this will work better. The next interpretation, I'm going to ask you some questions, and it'll come at you as either a question or a claim. I might ask the question, is mu equal to 3.0? And to answer this question, I want you to take a look at, the interval. What do you think? Is mu equal to 3.0? Look at those numbers, 3.144 to 3.256. 3 doesn't fall in there. So it's going to be tempting to say, no, I don't think mu is equal to 3. Well, first, you can do better than I don't think. We are 92% confident. That's what I want you. I want you to state your confidence. We are 92% confident. And rather than say that the average GPA differs from, tell it exceeds. Look, every single one of these values in this interval here are bigger than 3.00. We are 92% confident the average GPA exceeds 3.00. Is mu equal to 3.5? Is mu equal to 3.3? Is mu equal to 3.4? Each of those instances, 3.3, 3.4, 3.5, fall above the interval. We are 92% confident the average GPA is less than 3.3, is less than 3.4, is less than 3.5. Is mu equal to 3.1? We are 92% confident mu is bigger than 3.1. How about 3.15? Is mu greater than 3.15? How about if I ask, is mu equal to 3.15? How would you answer that question? And what I'm getting at with the questions is the point I'm asking you about. The 3.15, where does it fall relative to the endpoints? Is it inside or is it outside? When it's outside, like it is in the case where I'm asking about 3 or 3.5, we're going to be able to make a strong statement. We're 92% confident the average GPA exceeds 3.0. We're 92% confident the average GPA is less than 3.5. But when the value I ask about falls inside, 3.15 is in between these endpoints. 3.25 for that matter would be inside. That's when we're going to say, ooh, I'm not sure. At the 92% confidence level, the average GPA might be 3.15. It might be bigger than 3.15. It might be less than 3.15. I'm not sure. This is our official, this is the way we're going to say, I don't know. At the 92%, maybe, might be 3.15. Is mu equal to 3.2? Well, at the 92% confidence level, the average might be 3.2. I don't want to say it's equal to 3.2. Sometimes we think of these confidence intervals as a set of believable values for mu. That doesn't mean it's any one value. It's not 3.15 or 3.2 or 3.24. It's not any specific value, but it might be. Is it 3.0? I'm 92% confident it's bigger than 3.0. Is it 3.3? I'm 92% confident it's less than 3.3. Is it 3.21? Well, it might be. At the 92% confidence level, the average GPA might be 3.21 I just said. And so that's the way I want you to answer the questions or make statements about claims. Somebody claims the average GPA is 3.27. We're 92% confident the average GPA is less than 3.27. We don't believe that person. And so that's how I want you to answer questions or make claims about confidence intervals. So that is a pretty good introduction to the confidence interval technique. Now, I've looked at it in the context of a population mean, a large sample confidence interval for a population mean. You're going to see all the other confidence intervals we look at this semester. They're just variations of this one. So hopefully that's a good start. The two parts together, I think, added up to a little bit over 30 minutes. So hopefully that's some good information. It's kind of a weird time for me to say this, but hopefully you'll have watched these videos prior to returning to class, because I'm going to start doing some examples and seeing what you know. Thanks for tuning in. I'll talk to you soon.